Everyone, today I want to show you how to add and subtract rational expressions. We did multiplying and dividing earlier, and this is a little bit harder, so that's why it's coming second. I know it's weird to think of addition and subtraction as harder, but just think of what fractions are like, right? Multiplying and dividing is easy. Adding and subtracting is a little hard. Guess what step one is? Factor everything, just like usual. All right, moving along. All right, so here are a couple of examples. Now, technically, this first one is a rational expression, but the thing I want to get across is that we already know how to add these, right? We got to get a common denominator before we can add fractions. And so, getting a common denominator, well, I want to do that with this pair of numbers, just to show you how it's exactly the same, or very, very similar, I should say, in the case of rational expressions with variables in them. So the idea here is that I need to get some number that both 18 and 30 go into. And the way I'm going to do that is by multiplying both of them by whatever they are missing. So I'm gonna go over here. So 18 and 30. So we get 18. And we're going to find we're going to do a factor tree. We're going to get the prime factorization. So this is 2 times 9 and 3 times 3, 30. 2 times 15, which is 3 times 5. So 18 is 2 times 3 times 3, and 30 is 2 times 3 times 5. So the way I want to look at this is the thing that 18 is missing is this 5 here. And the thing that 30 is missing is one of the 3s, right? It's only got 1 3, it needs 2 of them. So what I need to do is figure out, I need to multiply both things by whatever they're missing. Now, you can see that in the LCD, right? So if I were to find the LCD here, the way I showed you to do it before was to just start with one of them and throw in whatever else you're missing. So I'm going to start with the 18. So 2 times 3 times 3. And then I'm going to throw in the thing that I'm missing, or all the things that I'm missing, which in this case is just 5. Now, I could multiply that all out, but I don't care to, because it doesn't really matter. I want to think of, well, okay, to get the LCD here, I need to multiply this by 5 and this by 3, because that's what they're missing. So that's what I'm going to do. I'm going to go multiply the 18 by 5 and the 30 by 3, or I should say multiply the numerator and denominator by those things. So this is the same thing as 5 over 5 times 5 over 18 plus 7 over 30 times 3 over 3. Right, I'm multiplying by whatever I was missing. Now, they both turn out to be 90, right? So this is 25 over 90 plus 21 over 90. I wrote 40, that's 90. Ugh, whatever. So this is 46 over 90. Now, we're not actually done yet, because one thing you might notice is, even though both of these started in lowest terms, when we added them together, we got something that wasn't in lowest terms. So I want to reduce my fraction, right? So they're both even. So this is going to be 23 over 45, and I can't reduce that anymore, so I'm done. All right, so that same set of stuff is going to happen with these. Now, one thing that you can think about is rewriting this as 1 over 2x y plus 5 over, if you do a factor tree for 16, you'll find that it's 2 to the 4th. So I'm just going to write it as 2 to the 4th. 2 to the 4th. Well, I guess I'm not. I guess I'm going to write it as 4 2s. 2, 2, 2, x, y, y, z. Right? And you certainly don't have to write it all out this way. I just wanted to show you that I'm really thinking of 16 not as 16, but as 4 copies of 2. That's really the way I want to think of it. And so what I need to do is ask myself, all right, well, what am I missing from each one? Okay, so if I were to find the LCD, which I will, LCD is, well, I need 4 2s, and I need 3 x's, and 2 y's, and a z. So 2, 2, 2, 2. And 3 x's, and 2 y's, and a z. And I'm not going to write it out like this most of the time. I want to think of this as 2 to the 4th, x to the 3rd, y squared, z. right? That's what exponents are for. They tell us how many times we're multiplying things. So I want to use them. And then I just have to multiply by each one by whatever I'm missing from the least common denominator. So when I multiply the top and bottom here of 1 over 2x cubed y, I need 3 2's. I got all the x's. I need a y and, or yeah, 1 y and 1 z. So I didn't really leave myself enough room. I better go to another page. So we got 1 over 2x cubed y, 1 over 2x cubed y, plus something that I have forgotten and is all the way back to the beginning. I wish I could just pick the page number here and zoom. 16xy squared z. 16xy squared z. And I have completely forgotten what the numerator was. Was it a 1? It was a 5. Okay. Okay. So I need to multiply by whatever I'm missing. That means that for the first fraction, I was missing 3 2's. Oh my gosh, that's not anywhere enough room. Oh, hang on, I think I can move this. One more try. Yes. Okay, great. Okay. So what I'm going to do is multiply by whatever I'm missing. So in the first case, that was 3 2's, which is 8. I have all the x's. I'm missing a y, and I'm missing a z. I have to multiply the numerator by the same thing, otherwise it changes the value, of course. And then over here, I was missing, well, I have all the 2's. I need 2 more x's. I have all the y's, and I need and I've got the z. So is it just x squared that I'm missing? Yes. Okay, so then I'm going to get 8yz over my denominator, 16x to the third, y to the second, z, plus 5x squared over 16x to the third, y squared, z. And now when you add them, you might ask yourself, well, how can you combine 8yz and 5x squared? The answer is you can't, so you don't. This is just 8yz plus 5x squared. That's a 2, I promise. Over my denominator, 16x to the third, y to the second, z. And maybe I should have left the 16 as 2 to the fourth the whole time, just to show you that whether you're doing this with numbers or letters really does not matter at all, right? If it's 2 to the fourth or 2 to the third or x to the third, those are, you know, from an operational standpoint, those are pretty much the same thing. We're doing the same thing with them. So that's what we're going to do. We're going to find the LCD for each expression that we're trying to add or subtract. And then we're going to multiply by whatever we're missing from each of the rational expressions, and then they'll all be over the same denominator, and then we can add them all up or subtract them all. So let's do a few examples. I hope I left myself a little bit more room. Oh yeah, 1 per page. That's about right. All right. So here's a nice simple one. So when I'm looking at the denominators here, well, they've both got an x minus 1. This one has a 2x plus 3. That one has an x plus 1. So I need to make them the same. So my LCD is going to be, well, they both have an x minus 1, but I need a 2x plus 3 from the first one and an x plus 1 from the second one. So that's my LCD. So we're going to multiply by whatever we're missing. So I'm going to multiply the first one by x plus 1 over x plus 1, and the second one by 2x plus 3 over 2x plus 3. So we're going to have x plus 1 over x plus 1 times 6 over x minus 1, 2x plus 3. Now watch the minus sign, right? Because the negative has to get distributed. So this is going to be x plus 4 over, we're multiplying by 2x plus 3 here, 2x plus 3 over 2x plus 3. And then this was x plus 1, x minus 1. Now, I will say this. Don't multiply everything out until you have to. Now we're going to have to multiply this top part out because we're going to want to distribute the negative to everything. And so we're going to have it all multiplied out so the negative distributes properly. So my first one, I'm going to have 6 times x plus 1 minus, and watch the parentheses here, x plus 4, 2x plus 3. All over my LCD, which I'm just going to do this. This is usually how I go about doing this, just so I don't have to write everything every time. And then I'm going to have to multiply out this top and combine all the like terms, right? So I'm going to have 6x plus 6, figure out what this is, distribute my negative through. I need a piece of scratch paper for that, or scratch screen, I guess. So we're going to have 6x plus 1 times, I forgot. My brain has deserted me here. Oh no, that was my previous scratch screen. X plus 4, 2x plus 3. Okay. Okay, so I'm just going to multiply everything out. So this is going to be 6x plus 6, and watch this minus sign. Don't just stick the minus sign and then write everything. What you want to do is parentheses, because the minus has to go on everything. So we're going to have 2x squared, then I'm going to have 8x plus 3x is 11x plus 12. So the minus needs to get distributed to everything in here. So I'm going to add 6x plus 6 minus 2x squared minus 11x minus 12. And I'm going to rewrite in descending order. So we're going to get minus 2x squared. 6x minus 11x is minus 5x. Plus 6 minus 12 is minus 6. Okay, now we want to try to refactor that, because sometimes when you do this, it'll all factor out and then you can cancel out more stuff. So you have to be careful. It only happens maybe 20% of the time. It's not super common, but it happens often enough that you do have to check every time. So I'm going to factor a negative out of this, just to make it look a little simpler. 2x squared plus 5x plus 6. All right, so I can't tell if that factors or not. I'm going to show you 2 ways to tell if it factors. One of them is going to be pretty simple. The other one's going to be a thing involving the quadratic formula. So if I want to check to see if that factors, I can do AC method, right? The AC method, if something factors, the AC method will always work. So I can do 2 times 6 and get 12. And I need 2 numbers that multiply to be 12 and add up to be 5. So 1 and 12, or 2 and 6, or 3 and 4. And there is no way to make a 5 out of any of those. Right, so 3 and 4, no, because that's, you can make 1 or a 7. You can make a 4 or an 8 out of this, and you can make an 11 or a 13 out of that. None of that works. So this is not going to factor. Here's the other way you can tell if something factors. Think about the quadratic formula for a second. If you recall, this is when your answers come out to be integers or rational numbers, that means that you could originally have factored the quadratic that they came from, right? It would have been all integers or rational numbers in your factoring. If not, if this square root comes out to be something where you end up with a root in it, right? Like if this is root 4, great, that's 2, and the square root goes away. But if it's like root 6, well, there's nothing you can do with that, and then the original expression wouldn't have factored. So the way you can tell if the square root part is going to go away is if the stuff inside is a perfect square. So if this, the b squared minus 4ac, is a perfect square, then your polynomial factors. And if it's not, then it doesn't. So you can just find b squared minus 4ac and see if it's a perfect square. So in this case, that would be 25 minus 4 times 2 times 6, which is 25 minus 48, which is negative 23. So clearly not, right? Not only would the answers be radicals, but they would be complex because we're trying to take the square root of negative 23. So this does not factor, and I can just leave it like it is. All right, so let's go back to where we were before on page 3. There we go. Yeah. So this is negative 2x squared minus 5x minus 6 all over my LCD. I'll write it again this time. And I'm just going to leave it multiplied out. You could multiply back together, but you shouldn't, right? It's not wrong if you do. It's just you're doing extra work to make things worse. Because in general, it's better to have your polynomials factored out than it is to have them multiplied out, because you can see more information about them if they're all multiplied, or if they're all factored out into linear terms. So don't multiply this out. Certainly, if you do, I'm not going to mark you wrong, but it's better if you don't. Like there's really no reason to multiply it out, so I'm not going to. All right, so this is a pretty good example of a medium bad rational expression subtraction, right? It was subtraction. We got quadratic terms that we had to try and refactor. Everything was kind of messy and long. They do get worse, but this is about what you want to think of as a kind of messy. All right, so how about this? Well, you will probably not be surprised to note that step one should be factor everything. So I'm going to factor everything. T squared plus 3 does not factor. That's a squared plus something. Nothing you can do with that. My denominators, though, t squared plus 9t plus 20 and t squared plus 8t plus 16. We got that t squared plus 9t plus 20 and t squared plus 8t plus 16. That's a terrible t. All right, so I'm looking for two numbers that multiply to be 20 and add up to be 9. That's 4 and 5. And here I'm looking for two numbers that multiply to be 16 and add up to be 8. So 4 and 4. Right, or t plus 4 squared, of course. So this guy, the first one, the t squared plus 9t plus 20, is missing one of the t plus 4s. And then this one is missing the t plus 5. So my LCD here, LCD is going to be t plus 4 quantity squared times t plus 5. All right, so keep that in mind. We're going to go back to the page we were on, which is like page 4. Yeah, and I'm going to replace this as t squared plus 3 over, that was t plus 4, t plus 5. And this is plus 6 over t plus 4 quantity squared. That's plus 4 quantity squared. And then I'm going to multiply by the things that I'm missing, which was 1 over t plus 5. 4. I meant 4. And then this one was 1 over 1. What am I doing? Oh my goodness. Well, that's just terrible. Pardon me. I apologize. I am, for some reason, not multiplying the top, which was bad. That's what I should be doing. And then this second one here, same thing, right? Not 1 over, I don't know why I'm saying that. But t plus 5 over t plus 5. All right, so now what I've got is t plus 4 times t squared plus 3. So this is going to require some more scratch paper. So we got t plus 4 times t squared plus 3 over my LCD plus 6 times t plus 5 over my LCD. And we're going to have to multiply all of this nonsense out. So like I said, it gets messy sometimes. So we're going to have t plus 4 times t squared plus 3. And the other one was 6 times t plus 5. All right, so let me show you how I actually do this. Certainly you can just do FOIL, right? That. The way I usually actually multiply these out personally is I think to myself, well, what's the highest power going to be? Highest power here is going to be t to the third, right? Because I got two t's here and one t there. So I'm going to have, the only way to make a t to the third is t times t squared. So that's t to the third. Then I'm going to look for all the t squared terms. I'm just going to count down one every time. So the only t squared terms is 4t squared. T terms, we got plus 3t plus 12. And this guy is 6t plus 30. All right, so we're going to have t cubed plus 4t squared plus 9t plus, what is that? 42 plus 42. Okay, so if you recall, in the past, I've mentioned how you can tell if something is going to factor by grouping. Now, it's possible that this could factor in some other way, but we're not gonna worry about those ways, about those polynomials of degree greater than 2. So I know this doesn't factor by grouping because the ratio here of 1 to 4 is different than the ratio here of 9 to 42. So I guarantee you this does not factor by grouping. I will go ahead and do a couple steps of it anyway, just so you can see. So I'll group it up, well, t squareds times t plus 4. And the next one I can pull a 3 out, it's plus 3 times 3t plus 14, and we are stuck. So yeah, it's not going to factor by grouping. So if you have a cubic, don't even worry about factoring it any other way but grouping, or if it's a difference of cubes or something like that. So I'm just going to say we are stuck here. So I'll assume that this doesn't factor and just leave it like it is. So t cubed plus 4t squared plus 9t plus 42. All over, it was t plus 4 squared times t plus 5. There we go. I wrote squared here, making a lot of errors. Sorry. There we go. Okay. So again, that's another pretty good example of a messy one where there's kind of a lot of work to do, but that's actually pretty standard with these. They're just kind of messy and there's a lot of work to do. So this one's not so bad. This one is actually quite easy. So let's go ahead and do it. I do just want to show you some things you can do with negatives. So remember, we've got x minus 3 and 3 minus x here. And if you recall, those things are negatives of each other. So I'm not actually missing anything here. It's just that I'm subtracting in the wrong order. So one thing that I can do is pick either one of them, it doesn't matter which one, and multiply by -1 over -1, which effectively just changes the sign in the top and bottom. So I end up with x plus 4 over x minus 3 minus -1 over x minus 3. So remember, 3 minus x times -1 does give you x minus 3. Right? You just have to change the order. And then I'm going to notice that I've got minus a -1 times something. So I'm just going to cancel those minuses out. So this is much easier now, right? I have x plus 4 plus 1 over x minus 3. That's just x plus 5 for x minus 3. Nice and easy. So you can introduce an extra factor of -1 to things that are being subtracted in an order that you don't like, right? X minus 3, I like better than 3 minus x. So I'm going to multiply the 3 minus x by -1. Well, you of course can't just do that. You have to cancel it out with a -1 in the top as well. But there you go. That one's not so bad. All right. This looks messy-ish. This isn't so bad, actually. All right. So step 1, factor everything. Let's do that. So the only things to factor, 2 and x, no. X and x plus 3, no. 3x plus 18, I can factor a 3 out. And x squared plus 3x, I can factor an x out. I don't even really need another page for this, right? So 3 times x plus 6. And that guy is x times x plus 3. So yeah, so our LCD here is x times x plus 3. Right, looking at all three terms, I've got an x here, an x plus 3, and then x plus 3. So the first one's missing an x plus 3, the second one's missing an x, and the third one's not missing anything. So yeah, let's multiply that all out. So we're gonna get 1 over x plus 3. No, I keep saying 1. I mean x plus 3 over x plus 3 times 2 over x plus we're missing an x here, so x over x times x over x plus 3 minus 3 times x plus 6. I guess I should probably have put that back, huh? X times x plus 3. And I got to multiply out the 3x plus 18 because I need to combine like terms here. So I'm going to multiply everything out. So we're going to have x plus 3 times 2. It's going to be 2x plus 6 plus x times x is x squared. And then we got minus, and watch the parentheses here. We're going to have 3x plus 18. Right, we got to make sure that this minus gets distributed to all the terms. So be really careful with your minuses and use parentheses. And this is all over x times x plus 3. All right, so when I simplify this, I'm going to get x squared. Then my x terms, I got a plus 2x and a minus 3x is minus x. And then for my constant terms, I got a plus 6 and a minus 18, which is minus 12. Over x times x plus 3. And I think that top factors need two numbers that multiply to be negative 12 and add up to be negative 1. So negative 4 plus 3 will work. So this whole thing is, I'm going to leave myself just a little bit of room, x minus 4 times x plus 3 over x times x plus 3. And the x plus 3's cancel, and we end up with x minus 4 over x is the whole thing. So this is another reason why you want to leave the bottom factored out, is so that when you're canceling at the end, that's easier too. But just in general, just sort of a blanket rule of if you have a polynomial factored, don't multiply it out unless you really got to, because it's going to be easier to work with, especially canceling like this, if you have it factored out. Sometimes you have to, right? We have to multiply this 3 times x plus 6 out so that we can combine our like terms. But basically, if you need to combine like terms, that's when you multiply it out. If you want to try and cancel or multiply, then you want to leave it factored. So there you go. And I think that's really all I want to say here. Let me make sure I don't have another example. No, I don't. That's my scratch work. Yeah, that's really all I want to say about adding and subtracting. Let me go back to the beginning. Well, page 2, I guess. Well, page 1. Factor everything. Do factor everything. Page 2. You want to find your LCD? If necessary, sometimes they start with the same denominator and then everything's super easy. But in general, you want to find your least common denominator, and then each factor gets, or each term gets multiplied by whatever the denominator is missing out of the LCD, right? So when the LCD was 2 to the 4th, x to the 3rd, y to the 2nd, z, well, I have a 2, 3 x's, a y, or 1 y, and no z. So I need 3 more 2's, another y, and another z. So that's what I multiply by. Here I'm missing 2 x's, and that's it. So we get x squared and x squared. So that's the key. Factor everything. Find your least common denominator. Multiply all of the terms so they have the same denominator, which is the LCD. Sometimes this gets messy. Most of the time this gets messy. Then combine all your like terms together and see if anything refactors, which it might, right? It could do like we did on page 6 here, right? So sometimes when you get to the end, this bit here will factor out and then you can cancel more. So you got to check that. It doesn't happen super often, but sometimes it does. And that's it. That's how you add and subtract rational expressions. So I think that is all I want to say. So I'm going to stop there. All right, I'll see you guys in the next video.